This section on Class B multi-engine performance will deal with the regulations for all phases of flight for that class of aeroplane. The regulations are all found in OPS 1, which we discussed briefly in the lesson on performance standards. However, most of these regulations can also be found in CAP 698. In this first lesson, we will discuss the regulations which are associated with the takeoff phase of flight. However, first of all, there are some general considerations we need to discuss before the takeoff regulations are examined. Paragraph 1.1 of CAP 698 on page 1 of section 3 simply describes the specimen aeroplane used in the CAP 698 manual. The specimen aeroplane for Class B multi-engine performance is a Piper Seneca 2. CAP 698 confirms that this aeroplane is classified as Performance Class B, and goes on to remind you in paragraph 1.2 of the definition of a Class B aeroplane. Class B aeroplanes are all propeller-driven aeroplanes having 9 or less passenger seats and a maximum takeoff mass of 5,700 kilograms or less. CAP 698 also states that performance accountability with one engine inoperative need not be considered below 300 feet. Further down on page 1 of section 3 are the regulations specific to the takeoff phase of flight. There are 2 principal regulations that must be complied with for takeoff. The first relates to the minimum field lengths that must be available for takeoff, and the second relates to the climb gradient after takeoff. This latter requirement will be dealt with in the next lesson. These takeoff requirements are exactly the same as those for the single-engine Class B aeroplane. The takeoff requirements state that if no clearway or stopway is available at the airfield, the takeoff distance, multiplied by 1.25, must not exceed the length of takeoff run available. This is best understood looking at an example. Let us assume that the aeroplane flight manual gives the takeoff distance as 4,000 feet. Multiplying this value by 1.25 gives us a value of 5,000 feet. Essentially, this means that the runway must be at least 5,000 feet long, or, more correctly, the takeoff run available must be at least 5,000 feet long. This rule ensures that once the aeroplane has completed the takeoff, that is, when the aeroplane has reached the screen height, there should be a certain amount of the runway still remaining. Therefore, the regulation requirement provides a safety margin for the takeoff. We discussed these safety concerns during the lesson on performance standards. The strict interpretation of this particular regulation is that although the actual takeoff distance is 4,000 feet, the authorities are suggesting that the worst case in a million would be a takeoff that is 5,000 feet. This fact helps us to see the difference between net and gross performance. Here, the gross performance for takeoff is 4,000 feet, but the net performance, which is always worse than the gross performance, is 5,000 feet. If there are stopways and/or clearways, then the requirements are a little more complicated. At airfields with stopways and/or clearways, there are 3 regulatory concerns about the takeoff distance. Firstly, when a stopway and/or clearway is available, the takeoff distance must not exceed the takeoff run available. Secondly, the takeoff distance, when multiplied by 1.3, must not exceed the accelerate stop distance available. Thirdly, the takeoff distance, when multiplied by 1.15, must not exceed the takeoff distance available. Since these regulations may be a little complicated to understand, let's work through an example to illustrate their meaning. We will assume a takeoff distance of 4,000 feet. The first regulation tells us that the takeoff distance of 4,000 feet must not exceed the takeoff run available. Therefore, the pilot must ensure that the runway, or more correctly the takeoff run available, is at least 4,000 feet long. The second regulation tells us that when the takeoff distance is multiplied by 1.3, that distance must not exceed the accelerate stop distance available. You may recall that the accelerate stop distance available is the takeoff run available plus any stopway. So, a pilot must ensure that the airfield has an accelerate stop distance available of more than 5,200 feet long. The last regulation tells us that the takeoff distance, when multiplied by 1.15, must not exceed the takeoff distance available. You may recall that the takeoff distance available is the takeoff run available plus any clearway. Therefore, the pilot must ensure that he has at least 4,600 feet of takeoff distance available. If any of these regulations cannot be complied with, the pilot must reduce his takeoff distance. The most practical method of doing this is to take off with less weight. Perhaps use a higher flap setting, or wait till the air density is increased to increase the aircraft's performance. Having discussed the regulations detailing the maximum takeoff distance that may be permitted at an airfield, this next part of the lesson will detail the regulations governing how the takeoff distance is corrected for non-standard conditions. These regulations stipulate what correction factors must be applied to the takeoff distance when the runway conditions are different from standard. On page 1 of section 3, under paragraph C in the CAP 698, it states that if the runway is other than dry and paved, the following correction factors must be used when determining the takeoff distance. These correction factors are shown on screen. As you have learnt already, grass runways will increase the takeoff distance compared to paved runways. Here, the factor to account for the effect of dry grass on the takeoff distance is 1.2 and 1.3 if the grass is wet. Point D details the corrections to be applied if there is a slope to the runway. Point D states that a pilot must increase the takeoff distance by 5% or by a factor of 1.05 for every 1% upslope. However, it also states that no factorization is permitted for downslope. In other words, if an aeroplane is to take off on a downward sloping runway, no correction factor is to be applied for the downslope. The reason for ignoring the downslope is because a downslope will decrease the takeoff distance. This adds a little extra safety margin to the takeoff distance calculation. This part of the lesson will deal with how the aeroplane's takeoff distance is actually calculated. Shown on screen is an example of the takeoff performance information. The example graph we will use is figure 3.1 on page 3 of section 3 of CAP 698. Firstly, the title of the graph indicates that the graph is for calculating takeoff with normal procedures. For other procedures, like maximum effort takeoffs, you may have to consult another graph. Next, take a look at the associated conditions, paying particular notice to the power and flap settings, as shown here. Also notice that this graph assumes a runway that is paved, level, and dry. If the conditions required for a given calculation are different, corrections will need to be made to the values that this graph will give. We saw these correction factors earlier. Notice the liftoff and obstacle at speeds. In this case, the obstacle at speed is the takeoff safety speed. A pilot must adhere to these accurately because they are the speeds which have been used to construct this graph. If a pilot were to deviate from these speeds, the required aircraft performance would actually not be achieved. Having looked at the various bits of information around the graph, let's now examine the graph itself. In the example, we will assume a temperature of 15 degrees at an airfield which is at a pressure altitude of 4,000 feet. To use the graph then, move upwards from 15 degrees until you have reached the 4,000 foot pressure altitude line. Then move right until you meet the reference line, shown here. The next variable is mass, or weight. In our example, let us assume a weight of 3,400 pounds. From the reference line, we must move down using the sloping guidelines until we reach 3,400 pounds, as shown here. From this point, we go horizontally to the right until the next reference line. The next variable is wind. In our example, we will assume a 10-knot headwind. Notice, though, that the slopes of the headwind and tailwind lines are different. We therefore recognize the 150% tailwind and 50% headwind rules that you have learnt about in the general principles for takeoff have actually already been applied. Travel down the headwind line until you reach 10 knots headwind, and then move horizontally right once more up to the last reference line. Remember that the takeoff is not actually complete until the aeroplane has reached the 50-foot screen height. So from this point on the graph, we must move up the guidelines to the end. The takeoff distance in our example is approximately 1,550 feet from brake release to the 50-foot screen, and the takeoff roll, or ground roll, is 1,250 feet. However, let us now assume that the runway has a grass surface and that the grass is wet. Remember that both these variables cause an increase in the takeoff distance. Since the graph assumes a paved dry runway, we will have to make a correction to the takeoff distance for the different conditions. You may recall that wet grass increases the distance by 30%, or by a factor of 1.3. Our calculated takeoff distance was 1,550 feet. But correcting it for wet grass would now make the distance 2,015 feet. Let us now assume that the runway has an upslope of 1%. You may recall this would increase the takeoff distance by 5%, or by a factor of 1.05. This now makes the total gross distance 2,116 feet. To comply with the regulations, you will recall that the takeoff distance must be compared to the available distances at the airfield to ensure it does not exceed the limits laid down by the authorities. To remind you of these regulations, turn to page 1, section 2 in CAP 698. The remaining pages in the multi-engine takeoff section of CAP 698 are the takeoff distance graphs themselves, and various examples on actually how to calculate the takeoff distance or maximum permissible mass for takeoff. There are also some graphs for calculating the accelerate stop distance required. Although the accelerate stop distance graphs are shown in CAP 698, there is no requirement for a multi-engine Class B aeroplane to demonstrate performance accountability of engine failure below 300 feet, and therefore there is no requirement to demonstrate the accelerate stop distance. However, a prudent pilot will check the accelerate stop distance required by the aeroplane in the event of an abandoned takeoff so that it will be shorter than the accelerate stop distance available. On page 2, section 3, is an example you may follow to calculate the takeoff distance. Page 3 of section 3 is the takeoff distance graph, but without flap, which we have already used and worked through. Page 4 of section 3 describes how to determine the maximal permissible mass to meet all the regulatory requirements, an example of which is on page 6. Lastly, on page 7, we find another takeoff distance graph, but this time assuming a maximum effort takeoff, which uses a higher flap setting. And on page 8 is the corresponding accelerate stop distance with this higher flap setting. You use these last two graphs in an identical way to the one you have already worked through. You will need to practice using all these graphs, so ensure you work through the examples in the CAP 698 and those in the questions for each lesson. Doing this will help you improve your accuracy in the use of the graphs and help to consolidate your knowledge of the principles we have considered so far. The last part of the lesson will focus on some of the certification specifications for multi-engine Class B aeroplanes. These can be found in the EASA document CS23. There are only two main specifications that apply to the takeoff phase of flight, and these specifications concern the takeoff speeds. The first of these certification specifications concerns VR. The specifications state that for twin-engined land planes, VR must not be less than the greater of 1.05 VMC or 1.10 VS1. VMC is the velocity of minimum control, which means the minimum control speed with the critical engine inoperative. VS1 means the stall speed, or minimum steady flight speed obtained in a specified configuration. The second of the certification specifications concerns the speed of the aeroplane at the screen height. The specifications state that for twin-engined aeroplanes, the speed at 15 meters or 50 feet above the takeoff surface must be the highest of three speeds. Firstly, a speed that is shown to be safe for continued flight under all reasonably expected conditions, including turbulence and complete engine failure. Secondly, 1.1 VMC, and thirdly, 1.2 VS1. The certification regulations concerning VR and the takeoff safety speed are not found in CAP 698 and therefore must be committed to memory. This completes the lesson on the takeoff for Class B multi-engine aeroplanes. Familiarize yourself with the format of the aircraft you are flying and correctly adjust the calculated takeoff distance for any variable that is not accounted for in the data. An understanding of the various conditions and factors that control the takeoff will better equip you to ensure that all your takeoffs are well within the limits of the runway available. In this way, you will minimize any chance of an accident occurring. Lastly, do not forget to check the regulatory requirements for the takeoff distance of the aeroplane you're flying.
In this lesson, we will concentrate on the regulatory requirements for Class B multi-engine aeroplanes in the climb. These regulations are applicable only to the operation of multi-engine aeroplanes in the commercial transport category. The takeoff climb requirements for Class B multi-engine aeroplanes are contained in EU OPS 1. But as for the takeoff requirements in the previous lesson, the climb regulations can be found in CAP 698 on page 9 of section 3. There are two main regulatory requirements which must be satisfied for multi-engine Class B aeroplanes. Firstly, the aeroplane must demonstrate that it can clear all obstacles within the takeoff climb path, and secondly, that it can achieve and maintain the minimum regulatory climb gradients. We shall discuss the obstacle clearance regulations first, and for this we will use the original wording in EU OPS 1, as opposed to the abbreviated version of the regulations in CAP 698. In EU OPS 1, we read that an operator shall ensure that the takeoff flight path of aeroplanes with two or more engines, determined in accordance with this subparagraph, clears all obstacles by a vertical margin of at least 50 feet. The takeoff flight path that this regulation refers to begins at 50 feet above the surface and ends at a height of 1,500 feet above the surface. However, there are several conditions that must be considered when complying with the 50 feet vertical clearance requirement. The first of the compliance conditions is that the aeroplane is not to be banked before it has reached a height of 50 feet above the surface, and that thereafter the angle of bank is not to exceed 15 degrees. The second compliance is that failure of the critical engine must be assumed to occur at the point on the all-engine takeoff flight path where visual reference for the purpose of avoiding obstacles is expected to be lost. Thirdly, the gradient of the takeoff flight path, from 50 feet to the assumed engine failure height, is to be equal to the average all-engine gradient during climb and transition to the en route configuration, multiplied by a factor of 0.77. Making this correction to the gradient gives a net gradient. The fourth condition of compliance is that the gradient of the takeoff flight path from the assumed point of engine failure to the end of the takeoff flight path is to be equal to the one engine inoperative en route climb gradient shown in the aeroplane flight manual. Finally, the regulations require that not more than 50% of the reported headwind component, or not less than 150% of the reported tailwind component, is to be used. The best way to gain an effective understanding of these compliance rules is to work through several examples. Before we look at the compliance issues, let us examine how to calculate whether a pilot will achieve the required obstacle clearance of 50 feet. In order to calculate this, various items of information are needed. Shown on screen is an example aeroplane at the 50 feet screen height, with a representative obstacle of 750 feet above ground level and 9,000 feet away from the aeroplane. In order to calculate the vertical distance the aeroplane will gain, and therefore work out the obstacle clearance, the gradient of climb achieved by the aeroplane needs to be known. This gradient can be extracted from a graph or table in the aeroplane flight manual. On screen is an example climb graph for a multi-engine Class B aeroplane. This graph can be found on page 13 of section 3 in CAP 698. Working through the graph, let us assume the temperature is 10 degrees Celsius at an airfield 8,000 feet above mean sea level and a weight of 4,750 pounds. It can be seen that the all-engine rate of climb is 1,330 feet per minute. This equates to an approximate climb gradient of 12%. This is the gross gradient. EU OPS states in the Obstacle Clearance Compliance Rules that the all-engine gradient must be factored by 0.77 to produce the net gradient. Multiplying 12% by 0.77 produces a net climb gradient of 9.24%. The gradient should also be corrected for wind by applying 50% of any headwind component and 150% of any tailwind component. But for simplicity, here we shall assume a zero wind condition. Using a climb gradient of 9.24% would mean that the aeroplane would gain a height of 832 feet in a horizontal distance of 9,000 feet, but the aeroplane's total height above the ground will be 882 feet, because the aeroplane is already at 50 feet. In this example, the aeroplane will clear the obstacle by 132 feet, which is well above the minimum clearance of 50 feet. The example we have just discussed changes dramatically if the pilot loses visual reference with the obstacle, perhaps because of a low cloud base on climbing away after takeoff. You may recall that one of the compliance conditions requires that failure of the critical engine should occur at the point on the takeoff flight path where visual reference for the purpose of avoiding obstacles may be expected to be lost. What this means is that when the aeroplane enters cloud, the assumed performance must be based on one engine only. In our example, let us assume the cloud base is at 500 feet. The aeroplane will climb at the all-engine gradient multiplied by 0.77 until cloud base is reached, as depicted on screen. However, at cloud base, the assumption is that the critical engine fails, and the gradient which must be assumed from this point is the one-engine inoperative gradient. The one-engine inoperative gradient can be obtained from the same graph that we used earlier. That graph is shown on screen here. The one-engine rate of climb works out to be 172 feet per minute, which equates to an approximate gradient of 1.54%. Returning to the example scenario, we see that climbing with a 1.54% gradient after it has reached cloud base, the aeroplane is not able to clear the obstacle. So in this case, during the flight planning stage, the pilot may have considered reducing the mass of the aeroplane in order to increase the climb performance. However, reducing the payload will reduce the revenue for the flight. So there is another way to solve this problem of being unable to clear the obstacle vertically. EU OPS 1 requires that if the obstacle cannot be cleared by a vertical margin of 50 feet, then the aeroplane must be able to demonstrate a minimum horizontal obstacle clearance. This horizontal clearance is calculated by using a simple formula. For a wingspan of 60 meters or more, the horizontal clearance is 90 meters plus 0.125 times d. For a wingspan of less than 60 meters, the formula is 60 meters plus half the aeroplane wingspan plus 0.125 times d. D is the horizontal distance from the obstacle to the end of the takeoff distance available, or the end of the takeoff distance if a turn is scheduled before the end of the takeoff distance available. When complying with the horizontal clearance regulations, for those cases where the intended flight path does not require track changes of more than 15 degrees, an operator need not consider those obstacles which have a lateral distance greater than 300 meters, provided that the flight is conducted under conditions allowing visual course guidance navigation, or if navigational aids are available, enabling the pilot to maintain the intended flight path with the same accuracy. For flights under all other conditions, horizontal clearance is 600 meters. For those cases where the intended flight path requires track changes of more than 15 degrees, an operator need not consider those obstacles which have a lateral distance greater than 600 meters for flights under conditions allowing visual course guidance navigation, or 900 meters for flights under all other conditions. Expressed more simply, these regulations are telling an operator that he needs to use the obstacle clearance formula only if the obstacle is within the lateral distances shown in the table. Let's work through an example to illustrate how the horizontal clearance requirements work in practice. The specimen aeroplane used in CAP 698 is the Piper Seneca, whose wingspan is approximately 12 meters. Therefore, in the formula, half the wingspan is 6 meters. D represented the distance from the end of the takeoff distance required to the obstacle, and in our example from earlier, we used 9,000 feet as being the distance to the obstacle, which is 2,744 meters. The formula gives us a horizontal obstacle clearance of 409 meters. Although the horizontal obstacle clearance formula tells us that the obstacle must be cleared by 409 meters, whether or not we use this figure depends on the margins and conditions shown by the table. Using our earlier example, the aeroplane is in the cloud, and therefore the pilot is unable to navigate visually. Therefore, the part of the table which concerns us here is the IMC row, which you see highlighted. Let's assume the aeroplane makes track changes of less than 15 degrees. This would mean that all obstacles within 600 meters of the aeroplane have to be considered. If an obstacle were to be within 600 meters from the aeroplane, that obstacle would have to be cleared by a horizontal margin of 409 meters. If the obstacle was further than 600 meters from the aeroplane, it would not be necessary to carry out the horizontal clearance calculation. In summary then, the rules state that the aeroplane must clear all obstacles by 50 feet vertically. If the aeroplane is unable to do this, then it must clear any obstacle within the obstacle area by a horizontal distance as calculated by using the horizontal clearance formula. We mentioned earlier in the lesson that there were two main requirements for multi-engine Class B aeroplanes in the climb. The first requirement concerned obstacle clearance, which we have just covered. The second part of the regulation deals with minimum acceptable climb gradients after takeoff. You may remember from an earlier lesson that the minimum climb gradients specified by the authorities are air gradients, and therefore independent of wind. EU OPS 1 states that, with all engines operating, the steady gradient of climb after takeoff must be at least 4%. The following special conditions have to be taken into account when demonstrating this gradient during certification. With one engine inoperative, the steady gradient of climb from an altitude of 400 feet above the takeoff surface must be measurably positive with these assumed conditions. From an altitude of 1500 feet above the takeoff surface, the steady gradient of climb must be not less than 0.75%, with these conditions assumed. The aim of these minimum climb gradients is to ensure that the aeroplane is operated within an appropriate safety margin. The maximum mass that will allow the aeroplane to attain the minimum gradients is called the climb limit mass. Exceeding this mass will mean that the aeroplane will not be able to attain these minimum regulatory gradients. Graphs which enable the pilot to calculate the gradient of climb are provided in most pilot operating manuals or aeroplane flight manuals. An example of this type of graph can be found in CAP 698 on page 13 of section 3. As with all graphs, before you use it, ensure you are familiar with the associated conditions applying to that graph. In this example graph, the assumed conditions are that the throttles are set at takeoff power, mixture is rich, and that flaps and gear are up. The climb speed for the graph is taken to be an indicated airspeed of 92 knots for all masses. We mentioned at the beginning of the lesson that obstacle clearance requirements and climb gradient requirements are published in EU OPS 1, and that abbreviated versions of these requirements can be found in CAP 698. We have already discussed these requirements, but we will mention them again as we read through CAP 698. These requirements are on page 9 of section 3 in CAP 698. At the top of the page, the first paragraph contains the definition that the takeoff climb extends from 50 feet above the surface at the end of the takeoff distance required to 1,500 feet above the same surface. The paragraph also mentions that takeoff power is applied for only 5 minutes, after which time maximum continuous power must be set. The next paragraph states that if the visual reference to the obstacle is lost, in other words, if the pilot enters cloud, it must be assumed that the critical engine will fail. The paragraph also specifies that all obstacles must be cleared by a vertical interval of 50 feet. The next sentence states that turns are not permitted before the end of the takeoff distance required, and thereafter must not exceed 15 degrees angle of bank. Paragraph 3.1.1 gives the formula for calculating the horizontal clearance that must be maintained if the aeroplane is unable to clear the obstacle by 50 feet vertically. However, only those obstacles within a certain lateral distance from the aeroplane, as shown by the table, need to be cleared horizontally by the distances calculated from the formula. Lastly, in paragraph 3.1.2, we find the climb gradient requirements for all engines operating and for one engine inoperative. Even though CAP 698 provides you with a lot of information, it does notably omit two very important requirements when considering obstacle clearance. The first piece of missing information is that you must factor the all-engine gradient by 0.77, and secondly, adjust the gradient for the effect of wind using the 50% headwind and 150% tailwind rules. Therefore, ensure you commit these regulations to memory. There are some example calculations in CAP 698 for you to work through and practice. For example, on page 12 of section 3, there is an example on how to calculate the horizontal distance travelled from the end of takeoff to 1,500 feet. On page 14 of section 3 is one other example. This example shows you how to calculate the aeroplane's vertical clearance of a given obstacle. The examples mentioned and the ones in the question bank are all important. They help you to practice the theory you have learnt and familiarise you with the types of questions that you may encounter in the ATPL exam itself. This completes the lesson on Class B multi-engine climb requirements. From this lesson, you should have learnt what the climb requirements are and also how to calculate your aeroplane's climb performance in order that you comply with the regulations. This lesson will focus on the Class B multi-engine performance requirements for the en route and descent stages of flight. Essentially, the en route part of the flight is considered to be from 1,500 feet above the airfield from which the aeroplane has taken off to 1,000 feet above the destination airfield. As with all the other requirements we have come across, the en route and descent requirements are written in EU OPS 1 and abbreviated into CAP 698. However, the abbreviated version in CAP 698 is very clear, and almost word for word like the original requirements published in EU OPS 1. Therefore, we shall work through the en route and descent requirements using CAP 698. At the top of page 17 of section 3, you can see the en route requirements. The first sentence simply reminds you what the en route stage of flight is. The requirement for the en route stage of flight is that in the event of engine failure, with the remaining engines set at the maximum continuous setting, the aeroplane must be able to continue flight at or above the relevant minimum safe altitude to an aerodrome at which the landing requirements can be attained. This requirement is almost identical to the single-engine aeroplane, the only difference being that whereas the single-engine aeroplane has to be capable of landing in a suitable field after engine failure, the multi-engine aeroplane must be capable of a higher performance, and therefore continue flight and land at a suitable airfield. Therefore, in the event of engine failure, the multi-engine aeroplane should have a level of performance such that it can, even with an engine failure, get to an airfield to land. However, as with other requirements we have covered, the en route requirements do have some compliance rules. In fact, these compliance rules are very similar to the ones we mentioned in the single-engine en route lesson. In order for the pilot to be able to abide by the regulations, the descent range with one engine inoperative must be known, as well as the one engine inoperative cruise range. Once these have been calculated, a flight track must be plotted that will ensure an airfield is always within the total one engine inoperative descent and cruise distance. Herein lie the compliance rules, because the compliance rules relate to how that descent range is calculated. The first compliance rule states that the aeroplane may not be assumed to be flying above the altitude at which the rate of climb is 300 feet per minute with all engines operating. You may recall from the single-engine en route lesson that this doesn't mean the aeroplane cannot operate higher than this altitude. It most certainly can. What the compliance rule means is the aeroplane must not use the extra altitude above the 300 feet per minute altitude to gain extra range to help comply with landing at an airfield after engine failure. The second compliance rule states that the one-engine inoperative net gradient of climb is the gross gradient of climb decreased by 0.5%, or the net gradient of descent is the gross gradient of descent increased by 0.5%. What the compliance rule is saying is that when calculating the descent range to work out if the aeroplane can make it to an airfield, the gross gradient of descent must be increased by 0.5%. This adjusted gradient is the net gradient, and it is simply adding a safety margin into the aeroplane's descent range. This is to ensure that the aeroplane will be at or above the relevant minimum altitudes for safe flight as stated in the operations manual, to a point 1,000 feet above an aerodrome. Calculating the descent range of a twin-engine aeroplane after engine failure is not as easy as it was for the single-engine aeroplane. For the single-engine aeroplane, to calculate the descent range, it was simply the height of the aeroplane divided by the gradient and multiplied by 100. However, the gradient of descent of a twin-engine aeroplane following engine failure is constantly changing. Let us explain why. Shown here is a twin-engine aeroplane, a Piper Seneca, in straight and level flight, with the forward force of thrust balancing the rearward force of drag. When the engine fails, notice that there is more rearward force than forward force, and as a result of the excess drag, the aeroplane will slow down if level flight is maintained. To maintain the speed, which should be kept at VMD, the thrust force generated by the remaining live engine must be augmented, so that the forces can once again balance. The only way to do this is to lower the nose, so that weight can act forward and provide enough weight-apparent thrust to balance the excess drag. If the nose is lowered by a sufficient amount, then the forces will once again balance, and VMD can be maintained. The only side effect is that the aeroplane is descending. However, as the aeroplane descends in the atmosphere, the air density increases. This means that the thrust being produced by the remaining engine increases, which reduces the excess drag. Notice now that there is no need for so much weight-apparent thrust, since the excess drag has reduced. To reduce the amount of weight-apparent thrust, the nose is raised a little. This process can continue until the remaining engine generates sufficient thrust to balance the drag without any need for weight-apparent thrust. At the altitude where this balance occurs, the aeroplane is able to level off. In summary then, after engine failure in the cruise, the aeroplane is forced to descend. But as it descends, the aeroplane can slowly reduce the descent angle until the aeroplane can once more fly level. This procedure is known as the drift-down procedure, and it produces a drift-down flight profile similar to the one shown on screen. It was stated that calculating the descent range for a twin-engine aeroplane after engine failure was complicated, and the reason, which is now hopefully apparent, is that the descent gradient or descent angle is constantly changing. In the absence of a drift-down graph, the only feasible way of calculating the descent range is to break down the profile into manageable segments and carry out several calculations, as shown on screen. Each of these calculations will need the net descent gradient at that altitude and the vertical interval of that segment. This will give the horizontal distance covered for that segment. To find the descent range, simply add all the horizontal distances in all the segments. After the descent range has been calculated, and the aeroplane is able to fly straight and level, the last remaining information that is needed is to find out the one-engine inoperative cruise range. Once this is known, it can be added to the descent range of the drift-down profile to give the total range of the aeroplane following engine failure. Therefore, at any point along the flight, there must be an airfield at which a landing can be made within the total range from engine failure. To ensure this, a circle, whose radius is the total single engine range, is drawn around each airfield between the departure and destination points. To comply with the regulations, the aeroplane track must fall inside these circles. In doing so, the aeroplane will comply with EU OPS 1, which states that in the event of engine failure, the aeroplane is capable of continuing flight at or above the relevant minimum altitudes for safe flight stated in the operations manual to a point 1,000 feet above an aerodrome at which the performance requirements can be met. If during some of this lesson you are unsure of the calculations and formulae needed to work out the horizontal descent distance using the gradient and height of the aeroplane, then please go through those parts of the climb and descent lessons in the General Performance Principles section that detail the use of these formulae. Practice using the formulae and go through the questions at the end of the lesson. These calculations form an integral part of the exam and your life as a pilot if you're flying Class B aeroplanes. You should have learnt two main points from this lesson. Firstly, you have learnt what the en route and descent performance requirements are that govern multi-engine Class B aeroplanes and where to find them. And secondly, that the pilot must comply with these regulations when operating a multi-engine Class B aeroplane in the commercial air transport category. This lesson will focus on the Class B multi-engine performance requirements for the landing stage of flight. There are two main regulation requirements. The first requirement is that the landing distance must not exceed the landing distance available. In other words, the aeroplane must be able to land within the length of the runway. This requirement can be called the landing distance requirement. The second requirement is that should the aeroplane be unable to land, it must be able to climb away from the aerodrome with an adequate climb gradient. This latter requirement can be called the landing climb requirement. As with other regulations we have dealt with in this course, the requirements relevant to the landing of multi-engined Class B aeroplanes can be found in CAP 698. However, caution must be exercised, since CAP 698 contains very abbreviated versions of the requirements, and therefore may be misleading. CAP 698 is, after all, supposed to contain supplementary information for examination purposes only. Let's discuss the landing climb requirements first. If, for whatever reason, a landing was not possible, then the aeroplane should have a level of performance that would enable it to climb safely away from the airfield. This must be possible with either both engines operating or with one engine inoperative. The landing climb requirements originate from the certification specification rules in CS23, but are adopted in a brief format into EU OPS 1. EU OPS 1 divides the landing climb requirements into all engines operating and one engine inoperative. With all engines operating, the steady gradient of climb must be at least 2.5%, assuming these conditions. Notice that in order to demonstrate this climb capability for certification and for operational purposes, the undercarriage is assumed to be extended and the wing flaps in the landing position. However, with the critical engine inoperative, the gradient of climb must not be less than 0.75% at an altitude of 1,500 feet above the landing surface, assuming these conditions. Notice this time that in order to demonstrate this climb capability for certification and for operational purposes, the undercarriage and wing flaps are assumed to be retracted. The reason that the critical engine inoperative gradient requirement is much less than the all-engine climb gradient requirement, and that the aeroplane configuration is cleaner, is because the failure of the critical engine results in an approximate 75% loss of climb gradient. Setting too high a level of regulation would impede on the operational capability of the aeroplane in terms of its payload, because if the aeroplane is unable to attain these gradients, then the weight of the aeroplane must be reduced to an amount which can allow the gradient requirements to be met. The term used to describe the maximum mass that can be carried and still attain the minimum gradient is the landing climb limit mass. We did mention earlier that the CAP manual shows the climb requirements. On page 17 of section 3 is the all-engine climb requirement, which in CAP 698 is called the balked landing requirement. This repeats that the gradient of climb must be at least 2.5%, and that this gradient must be achieved with these conditions. On the following page is the one-engine climb requirement, this time called the missed approach requirement. Remember that the minimum acceptable gradient must not be less than 0.75% at 1,500 feet above the aerodrome. Thankfully then, these landing climb gradient requirements need not be committed to memory. However, caution must be exercised. The climb gradient requirements mentioned here are specific to aeroplanes in the normal, utility and aerobatic category of more than 2,722 kilograms, and therefore only represent a portion of the requirements for multi-engine Class B aeroplanes. Having discussed the landing climb requirements, let us now turn to the landing distance requirements. In fact, these requirements are identical to Class B single-engine aeroplanes. EU OPS 1 states that an operator must ensure that the landing mass of the aeroplane, for the estimated time of arrival, allows a full stop landing from 50 feet above the threshold within 70% of the landing distance available at the destination aerodrome and at any alternate aerodrome. This means that the aeroplane must be able to land within 70% of the landing distance available. To help clarify this, let us work through an example. If the landing distance available at the destination airfield is 2,800 feet, then obviously the aeroplane must be able to land within 70% of 2,800 feet. To calculate this value, we must divide 2,800 feet by a factor of 1.43. Carrying out this simple calculation gives us an answer of 1,958 feet. 1,958 feet is 70% of 2,800 feet. Therefore, the aeroplane must be able to achieve a full stop landing within 1,958 feet. There is another way to look at the landing requirement. If the landing distance of the aeroplane is calculated to be 1,400 feet, what is the minimum length of the landing distance available, which will allow a pilot to comply with the 70% rule? In this case, we simply multiply 1,400 feet by 1.43. This gives us an answer of 2,002 feet. Therefore, the landing distance available must be at least 2,002 feet. If the destination aerodrome has a runway with a landing distance available in excess of 2,002 feet, the aeroplane will be able to land within 70% of the landing distance available, and therefore satisfy the regulation requirement. The 70% landing regulation helps us to see the difference between net and gross performance. Here, the gross performance is 1,400 feet. But the net performance, which is always worse than the gross performance, and is the 1 in a million worst-case scenario, is 2,002 feet. The landing regulation we have just been discussing can be found in CAP 698, midway down page 17 of Section 3. The regulation states that the landing distance from a screen height of 50 feet must not exceed 70% of the landing distance available. If the aeroplane cannot come to a full stop within this length, then the landing distance must be reduced, either by selecting a higher flap setting or simply by reducing the mass of the aeroplane. In Part 1 of the multi-engine landing lesson, you learnt about the landing climb regulations and the landing distance regulations. In Part 2, you will learn a few more regulations and how to actually calculate the landing performance using sample data from an aeroplane flight manual. Having discussed the regulation requirements detailing the maximum landing distance that must be available at a destination airfield or alternate airfield, we will now examine in detail the regulations governing how the landing distance is calculated, giving non-standard conditions. In CAP 698, Section 3, on page 17, under point 511b, we read that if the runway is of grass up to 20 centimeters high, the landing distance should be multiplied by a factor of 1.15. This would effectively increase the landing distance by 15%. Point C states that if there is an indication that the runway may be wet at the estimated time of arrival, the landing distance should be multiplied by a factor of 1.15. Again, multiplying the calculated landing distance by a factor of 1.15 will increase the landing distance by 15%. Point D states the landing distance should be increased by 5% for each 1% downslope. This means that for a 1% downslope, the landing distance should be multiplied by a factor of 1.05. Therefore, for a 2% downslope, the factor would be 1.1. Point D also states that no allowance is permitted for upslope. The reason for this is that upslope will reduce the landing distance. If a pilot were to ignore the reduction in the landing distance, then a margin of safety would be incorporated into the landing distance calculation. Lastly, point E states that there must be compliance with the dispatch rules for scheduled or planned landing calculations, and that these can be found in EU OPS 1.550, paragraph C. The dispatch rules, found in EU OPS 1.550, paragraph C, state that for dispatching an aeroplane, it must be assumed that firstly, the aeroplane will land on the most favourable runway at the destination airfield in still air, and secondly, that the aeroplane will land on the runway most likely to be assigned considering the probable wind speed and direction. If this second assumption cannot be met, the aeroplane may be dispatched only if an alternate aerodrome is designated, at which full compliance of the regulatory dispatch requirements can be met. These dispatch regulations may sound a little complicated, so let's examine them further. The first assumption is that the aeroplane will land on the most favourable runway in still air or zero wind. This means that, assuming zero wind at the destination airfield, the runway which would accommodate the largest possible landing mass would be selected, since this is the most favourable runway. In our example on screen, assuming zero wind, runway 04 and runway 22 both allow a maximum landing mass of 1,500 kilograms. But runway 31 and runway 13, being much shorter runways, allow a maximum landing mass of only 1,000 kilograms. Therefore, the most favourable runway in still air is either runway 04 or 22, which both allow a maximum landing mass of 1,500 kilograms. The second dispatch assumption is that the aeroplane will actually land on the most likely runway to be assigned, considering the probable wind speed and direction. In this case, runway 04 has a strong headwind for the landing, which will allow the aeroplane to land at a much greater mass than if there were no wind. In our example, the headwind has increased the maximum landing mass to 1,750 kilograms. However, runway 22 has a tailwind, which will decrease the maximum landing mass to 800 kilograms. Runway 31 and runway 13 both have a full crosswind. Therefore, the maximum landing mass for these two runways will be the same as for still air. If the second dispatch assumption is that the aeroplane will land on the runway most likely to be assigned, considering the probable wind speed and direction, then it would have to be runway 04, with a maximum landing mass of 1,750 kilograms. In summary then, the first assumption requires that the pilot select runway 04 or 22 for a maximum still air landing mass of 1,500 kilograms, and the second assumption will require the pilot to select runway 04 for a maximum landing mass of 1,750 kilograms. Now we need to consider what to use as the dispatch mass of the aeroplane. If the aeroplane was dispatched at 1,750 kilograms mass, and then on arrival at the airfield, the wind was less than forecast, the aeroplane would not be able to land. Therefore, the aeroplane must be dispatched with a mass of 1,500 kilograms. Dispatching the aeroplane with this mass would mean that, no matter what wind conditions prevail at the destination airfield, the aeroplane will have a mass which will allow it to land at the airfield. The way to simplify the dispatch rule is always consider the greatest mass in still air and the greatest mass in the forecast wind conditions, and of the two, take the lesser mass as the dispatch mass. Of the two, it is the still air mass that is usually the lesser mass, as shown in our example. The exception is when there is a tailwind on a unidirectional runway. A unidirectional runway is a runway whose direction for takeoff and landing is fixed in one direction. And in this case, the maximum landing mass in the tailwind will be less than the maximum landing mass in still air. This part of the lesson will deal with how the aeroplane's landing distance can actually be calculated. All aeroplanes will have either a pilot operating handbook or an aeroplane flight manual. The purpose of these manuals is to show not only how to operate the aeroplane, but also to detail the aeroplane's performance. Shown on screen is an example of the landing performance information. The example graph we will use is figure 3.9 on page 21 of section 3 in CAP 698. Always take a look at the associated conditions first, paying particular attention to the power and flap settings, as shown here. Also, notice that this graph assumes a runway which is paved, level, and dry. If the runway conditions required for a given calculation are different, corrections will need to be made to the values that this graph will give. We saw these correction factors earlier. Notice this area here, which highlights the barrier speed for different weights. This is actually the reference landing speed. The regulatory speed at the landing screen height is called VREF, and for a Class B multi-engine aeroplane, it has to be no less than the greater of VMC, or 1.3 times the stall speed in the landing configuration, 1.3 VSO. A pilot must adhere to the VREF speeds shown here, because they are the speeds which have been used to construct this graph. If a pilot were to deviate from these speeds, the required aircraft performance would not be achieved. Having looked at the various bits of information associated with the graph, let's now examine the graph itself. The left-hand carpet of the graph involves the variations in temperature and pressure altitude. This part of the graph accounts for the effect of air density on the landing distance. In the example, we will assume a temperature of 5 degrees Celsius at a given airfield situated 4,000 feet above mean sea level. To use the graph then, move upwards from 5 degrees Celsius until you have reached the 4,000 feet pressure altitude line. Then move right until you meet the reference line, shown here. The next variable is mass. In our example, let us assume a mass of 3,400 pounds and a VREF of just below 80 knots. From the reference line, we must move down using the sloping guidelines until we reach 3,400 pounds, as shown here. From this point, we go horizontally to the right until the next reference line. The next variable is wind. In our example, we will assume a 10-knot headwind. Notice, though, that the slopes of the headwind and tailwind lines are different. We therefore recognize that the 150% tailwind and 50% headwind rules that you learnt about in the General Principles for Landing lesson have already been applied. Travel down the headwind line until you reach 10 knots headwind, and then move horizontally right once more up to the last reference line. Remember that the landing starts at the 50 feet screen height. So, from this point on the graph, we must move up the guidelines to the end. The landing distance in our example, then, is approximately 2,000 feet from the 50 feet screen to the full stop. The landing roll, in other words the ground section of the landing, is just 990 feet. Let us now assume that the runway has a grass surface and that the grass is wet. Remember that both these variables cause an increase in the landing distance. Since the graph assumes a paved, dry runway, we will have to make a correction to the landing distance for the different conditions. You may recall that grass increases the landing distance by 15%, or by a factor of 1.15, and a wet surface also increases the landing distance by 15%, or by a factor of 1.15. Our calculated landing distance is 2,000 feet. But correcting it for grass means we need to multiply this by 1.15, and again by 1.15 because the grass is wet. This now makes the landing distance 2,645 feet. Let us now assume the runway has a downslope of 1%. You may recall this would increase the landing distance by 5%, or by a factor of 1.05. This now makes the total gross landing distance 2,777 feet. To comply with the regulations, you may recall that the landing distance must be within 70% of the available distance at the airfield. Therefore, multiply 2,777 feet by 1.43. This means that our landing distance available must be at least 3,971 feet. Before this lesson ends, let us briefly look at the pages in CAP 698 regarding the multi-engine Class B aeroplane for landing. Page 17 and 18 of Section 3 detail the landing distance requirements and climb gradient requirements that we have already examined. Near the top of page 18 is an example of how to calculate the one-engine outgradient using figure 3.7. The bottom half of page 18 is another example of how to calculate the climb gradient, but this time using all engines operating, and it refers to figure 3.8. Work through these examples, and especially how to change a rate of climb into a gradient, because the two graphs used in these examples do not directly provide a gradient. It must be worked out. Page 19 is the landing climb graph figure 3.8. This graph assumes both engines are operating. Again, this graph only provides you with a rate of climb. If you need to calculate the gradient to check whether you meet the all-engine climb gradient requirement, you must convert this rate of climb to a gradient. If you are unfamiliar with this conversion, either work through the examples of the previous pages which we just mentioned, or else consult previous lessons in the General Performance Principles section. Page 20 is an example you can work through, which is about how to calculate the landing distance required. And this example uses the normal landing distance graph shown on the next page, page 21, as shown here. On page 22, there is one more example, but this time, this example is how to calculate the maximum landing mass. This example uses the graph on the next page, which is the short field landing distance graph. Hopefully, you are now able to work through the landing graphs for Class B multi-engine aeroplanes and make the corrections to the graphs for any conditions that are not accounted for by the manufacturer. If you need further practice in using the graphs to increase the accuracy of the results, we suggest that you work through the examples in CAP 698 we just mentioned, or use the questions which test you on what you have learnt in this lesson. That concludes the section on Class B multi-engine performance. The next section of aircraft performance will focus on the Class A medium-range jet.